Have you ever wondered what you could do with a math degree? I mean, what do you do with a math degree besides become a math teacher? I'm sure that you've wondered at some point, when would you ever use this, meaning like math class? Um, there's a good answer to it. The answer is we're trying to teach you how to think. But there is a better answer too, that you can use and specialize in some skills that use mathematics. And I'm not just saying this, nobody paid me to say it, but it is actually one of the most marketable degrees. I've had some headhunters and people that place people into jobs and careers that someone with the math degree is very sought after. And they often, go figure, solve problems. Now, they solve problems that end up a lot of times in sort of the business world. And if you're looking for like a name, and even if you're not looking for a name, I'm going to give you not the name of someone that's hiring, but the person is typically called a management analyst. Companies hire a management analyst to solve problems. And then the work that they do varies from client to project. And often, as it says, when there's a problem, when like a management team finds a problem, they may call on someone like this. They could be a consultant, meaning that they would work like on their own, or they might be directly hired by a company and work for a company. But they figure out where and why the problem's happening, and they come up with a way to fix it. A lot of times, obviously, these things have to do with numbers. That type of problem, like how much of something should we make, or what's the predicted plan for this year. And it turns out that one such specific problem that they solve, and again, I'm not making this up because actually my wife's friend's husband, let me see if I got that right, my wife's friend's husband, he actually got employed by a company to do what we're going to do today, and they paid his way even through college as he was even starting to do this. And the thing that he did or does, and we're going to talk about today, is linear programming. It's not programming a computer, although that's also something that sometimes a math person might specialize in, but this is actually a process. It's a process that basically seeks after what we call the optimal value. It's a process that seeks after the best way, and we generally call that optimization. Now, you might want to jot this down on just regular notes, but keep that sheet of paper handy because it also has some notes on it that you won't have to jot down. Now, again, the guy does this, and although the problem that we're going to work through probably is a little simpler, and maybe he does it more with a computer and such, the overall process is the same. I can remember talking to him, although we didn't talk much about it. We enjoyed talking about fishing and other things too. But as he said, yeah, this is what I do. And so it's neat what you guys are going to see today. To kind of put it into a classroom setting, we say that our goal is to find X and Y. So we're going to find X and Y. And that sounds kind of like an algebra thing to do. But we're going to find X and Y that's going to maximize or minimize. There's that idea of being optimal. So we're going to try to maximize or minimize something called an objective quantity, which is an equation. Now you're going to find out as we go through this process that it actually takes just about everything we learned in this chapter and sort of ties it up into a nice little box into one problem. Honestly, if there's going to be one problem on the test next week, it would be this problem. Although there'll be other problems, this type of problem will be on there because it's going to use like everything we've done in this chapter, except partial fractions. Partial fractions is kind of a specific thing that's not directly related to this. Now, it's a process. It's got steps. I'm not typically a big step-by-step teacher, but I do like to show you these steps because we will follow them. They're on the back of your slip of paper, so I don't really think you need to write them down again, but look at them. And I also have them up here so that I can look at them and we can kind of look at them together, but we'll identify the unknowns. That's kind of the old what's X and Y equal. When you first start a problem, what's your unknown? What is X and Y? And then you're going to write what's called an objective quantity equation. A lot of times step 1 and step 2 go together because you'll find out the equation uses x and y. It's also something that's unknown, but it's unknown in a different way. So 1 and 2 is kind of getting your problem set up. Actually, number 3 is kind of getting your problem set up because you're going to also create something. It's kind of like the last problem on your assignment last night. You're going to create a system of inequalities. You're going to write greater than or less than. Now, once you get the problem set up, you're going to find that it's time to start solving it, which is to actually make a graph. It's going to seem natural because it's what you just did. There's those corner points. Okay, I promise those are the most important points because you're going to end up plugging those corner points into the objective quantity to end up with a max or min. You're going to find out that it's like the corner points are the extreme points of your solution. And if you think about it, extreme type numbers are the ones that could possibly give me my best answer, like my maximum or my minimum, depending on what we're looking for. All right. Now, the problem we're doing right now is a little more of a textbook problem. It's also sort of borderline silly because if you look at the numbers in it, you might wonder who sells and makes a phone for $9 and $6, but just pretend with me. It's a good math problem. Maybe it's a toy phone. Okay, maybe it's like a toy phone. But why don't you read the phone problem and maybe read it again? Seriously, just kind of read it, and then we will take this information and throw it into this process known as linear programming. Okay, lots of words, as some of you said when you came in. It's also kind of neat. Imagine that this is like your job to solve problems, and somebody's like, here's this information. What do we do? Do you realize that that's kind of the question? This is the last sentence. What mix of phones do we need to make? Okay, so I know there's a lot of information there, but the first thing you want to do is realize that there's kind of two things that this problem is sort of dependent on. That is the number of X phones and the number of Y phones. You should feel like that's really what we want to find. How many phones should we make? So we'll say that X can be the number of, now we could choose either one. Let's choose deluxe. And then Y can be the number of standard. Now it's important that you understand that X and Y represent a number of phones. It's not the color of the phone. It's not the cost of the phone. It's the number of phones. Do I make 5 of this and 6 of that, or do I make 2 of this one and 10 or 100? Okay, we have to go through the process to find this out. So this would be step 1. Now step 2 is also kind of like an unknown, but it's dependent upon X and Y. It's called the objective quantity. And the objective quantity is the thing that you're trying to maximize. If you read the last sentence near the end, it says to effectively generate profit. That's a fancy way to say we want to get the maximum profit. So the objective quantity is profit. Like it's a word, it's a number, but it's also an equation. And now we start to get into the problem. You should be kind of saying, okay, wait a minute, how much profit do I make on a deluxe phone? And it's in there, it's near the top. And how much do I make on a standard phone? And so we create a pretty standard equation, right? It's actually in standard form. You guys have written equations like this in this chapter to say something simple like 9x plus 6y. All right, now imagine if I knew what x and y was, then I could plug it in and find my profit. Ultimately, that's what we're going to do. But to find what x and y are to figure out the constraints of the problem. Now, the constraints of the problem is kind of all that mishmash in the middle of this paragraph. where it says we have this much or not that much, and we need to make sure those are the constraints. It's kind of strange, but I'm going to start with these because the next time you do this, you also will start with these two constraints. They're assumed constraints. I sort of hate that word in math, but they're something that we can assume because it's true that x has to be greater than or equal to 0. It's a simple statement that we're not going to have negative phones. Same thing with y. It has to be greater than or equal to 0. Now, what that technically does is it gives me a shaded region so far that's in quadrant 1. And you'll say, yeah, I mean, that would be the only thing that makes sense. But yes, they're part of the constraints. Now, somebody says, are they always here? I'll say that there's always some type of constraint about x and y. Okay, there might be a stronger statement, like it might say, wait a minute, we need to at least make 5 phones. So maybe it's x greater than 5. It doesn't say that, though, so we just kind of default to 0. Now, what about these machines? You got to understand that that's kind of like saying that there's people that work. Maybe it's the people that work the machines. There's only so many hours available. It takes more time to do something. So we have to put these numbers into these two machine constraints. And I'll help you a little bit. Let's do machine A. Machine A. Well, what do we have about machine A? It says deluxe phone requires 3 hours of machine A. It's like right in the middle there. It says deluxe phone require 3-hour machine A. If you read the next sentence, it says that a standard phone requires 2 hours of machine A. Now, I'm reading 2 sentences and grabbing a number of hours, 3 hours for a deluxe phone and 2 hours for every standard phone. But I grabbed that out of 2 sentences, and both of those have to do with machine A. And then if you read the next sentence, it says that machine A can only work for no more than 12 hours. It's a little tricky. Sometimes you just have to see it written down. Are you thinking, though? Are you thinking, where did I get those numbers from? Because I challenge you to see if you can do machine B. Just see if you can read carefully and get machine B. Okay, and it just requires reading, right, and trying to see where the numbers are kind of going to see that it's 1 hour for machine B, but it's still 2 hours. I'm sorry, it's 1 hour for every X phone on machine B and 2 hours for every Y phone on machine B. What do these two machines do? I don't know. It doesn't say. Maybe one of them sort of cuts out the phone and one of them colors the phone. It's pretty generic, right? I'm sure there's more that is needed than 2 machines. But for our problem, that's what we're given. Okay, so we only have so many hours that the machine can run. Now, what's really happening here is we have a system of inequalities that technically can be represented by a shaded region. I hope you understand as we go through this that the shaded region is really all the different combinations of phones that we could make. That's a pretty powerful statement. Did you think about that? We're going to make a graph. We're going to shade it in, technically representing every possible amount of phones that we could make. Okay, and then we're going to figure out which possibility is the best. Okay, but we need to graph these. And as I said yesterday, standard form, when you use using x and y intercepts with standard form is really nice. I'm not going to solve these equations for y equals because the first one I can plug a 0 in and see that y equals, or the y-intercept equals 6. And then the second, I can plug a 0 in for y and I can get the x-intercept to be 4. So pretty quick and simple. And I hope that you're saying yes to x and y intercepts. Now you should shade. Maybe you want to do it lightly, but really if I use a test point for this equation, I find out that I'm shading, if I use a test point at 0, 0, I find out that I'm shading on the true side. Maybe you're thinking about the other boundary line and shaded region. If you're plugging a 0 in, you get a y-intercept of 4. You get an x-intercept of 8. Feel free to double check. You want to make sure your boundary line is crisscrossing in this manner. And it's also a true test point. Now, we don't want to make any always statements like you always shade in this spot. What you do is you always shade where the solutions, where the shaded regions intersect. So just like yesterday, but we do end up with a nice little solution. Every point in that shaded region would satisfy the machines. Like, seriously, I could make one of each phone, 1, 1. If I make one of each phone, this machine's not going to be overworked and this machine's not going to be overworked. Do you see that? I could plug a 1 that's in there. But you should be saying, yeah, but I could make more than just one of each phone. Right. In fact, it's the corner points that end up being my extreme points that, if you think about it, would have to produce a maximum profit because they're like the biggest numbers and they're still solutions. Now, there's technically 4 corner points. 0, 0, although it is kind of silly, technically makes the list. So we're being technical. Again, if I make 0 phones, I satisfy the machines. I might also go out of business because I don't make any profit. But I could make, oh look, I could make all standard phones, 0, 4. I can make all deluxe phones, 4, 0. Or I can make a little bit of both. Now, the little bit of both, I'm sure you realize, is the intersection of the lines. And where have you heard that before? The intersection of the lines. It's called a system. And really, it's a system based off of our two standard form equations. Okay, you want to solve that system. If you have enough space and if you're comfortable, you could just solve it right here. I don't think you need a matrix to do that, do you? You could just throw a negative sign at that second equation. If you throw a negative sign on it, very quickly you see that 2x equals 4. So x equals 2. And you can obviously plug that back in to get the remainder, which is 3. Are you following what I did there? We found the intersection of those two diagonal lines by basically solving a system like we did the first couple days. I did mention that you probably don't need a matrix, but that doesn't mean you can't use a matrix. I'm just not going to bother right now. Okay, so we're getting close to kind of making our conclusion. What's our conclusion? We're trying to figure out the profits of each of these. So we go through a little process of plugging into the profit equation. Okay, again, if we make 0 of each phone, the profit is 0. Yes, you should list that because it's technically a corner point. Now, if you make all Y phones, but 0 deluxe phones, then I get $6 for every one of those standard phones. I get $6. Of course, $0 for the other one, but it's 24 bucks. That's more than I had when we started. So do you see the process I'm going through? I'm plugging in to my objective quantity. What if you become a all deluxe company? We're going to just make deluxe phones. We're going to specialize in deluxe phones. Now we make $36 profit. Again, getting better. What if we decide to do a little bit of both? Now, I'm showing a little bit of work here. I'm going to be honest, if you do some of this work on a calculator, it's not hard work, but okay, you still have to show the numbers, like you have to show your list and show your answer. This stuff in the middle It's kind of up to you, but I wanted you to see where I'm getting them. 18 plus 18. Oh, it's also 36. Now, this is an interesting scenario because we actually have what I would call like a tie. If I was going to go into the boardroom and sit down and talk to the CEO, I'd say, hey, CEO, we could make all deluxe phones and get $36. Maybe this is 36 million. That'd make a little more sense. Or we can make a little bit of both and we could still make 36 million. So what do you want to do? Well, what do you want to do is up to the company to decide. This is just the numbers. This is the analysis that we talked about that person that actually uses math on their job could do. But we make a little conclusion. For the classroom, we make a little conclusion. And I'd like you to write a little sentence. It would be something like this. It doesn't have to be exactly like I'm writing it, but something like maximum profit of 36. So we kind of identify. If you say, yeah, I already know that, but I want you to write that you know that. So maximum profit 36 with, and then here we have this kind of this strange scenario. We sort of have a tie with 4 deluxe, but 0 standard. Or, and again, because it's a tie, I kind of have to list 2 possibilities here. 2 deluxe and 3 standard. So we want you to do more than just circle your answer or write it as a point, although we know it is a point. I want you to kind of describe it. I want you to describe it. Okay, I know you may have done some problems like this in Algebra 2, but sometimes you see them again this year, and if you've never seen them before this year, you can see how we can take all these steps and kind of put them together. Makes for an interesting problem. It's also interesting to see if you can do one. That's the lumber problem. I tried to make up a problem that's similar enough, but yet different enough to allow you to explore and see if you can get this right. Now, I'm going to just be like a step behind you, so I encourage you to be trying to do it on your own, but I'm going to give you some feedback as we go. Now, although you can do it how you want, if you want to be able to compare with mine and just feel a little more in sync with what I'm doing, I decided to let X be lumber and Y be plywood. If you did it the other way, it's not wrong, but you might want to change it if you want to be able to just easily compare with my steps. Looks like you guys are well on your way here. I put the profit equation up if you want to take a glance, but it looks good. I expect that you have steps 1 and 2. Students usually quickly realize it's step 3 that's kind of the bugger. Step 3 is the one that you got to think. And the whole problem is really based off of how you set up your constraints. Try. Just try. I'm going to give you some feedback, but see if you can write them. As a little hint, you're only going to use each number once. So yes, you're using the number 200. It only shows up one time in one constraint. 300, you only use it once in one constraint. 800, same thing. You only use that number once and it shows up in one constraint. There's 3 constraints and each of those numbers gets used once.
That was my question.
Now, I know you guys are all at a different spot. Before you start making a graph, you might want to make sure that your constraints are right. So I'm going to show you, and it's kind of like, don't look unless you want to see, okay? Here's your constraints. This is a good example of upping the ante on the greater than 0 constraint. We were able to go stronger. It doesn't have to be just greater than 0. If you read the words carefully, how it says at least, that word at least kind of gets you to think greater than 200, greater than 300. This is an interesting graph. Just be very careful as you mark your points and your intercepts. You should be drawing some horizontal and vertical lines, right? Just mark those values with 200 and 300. And then you have one diagonal line. Don't shy away from finding the corner points. And you don't need like a heavy-duty calculator. You just need to think a little bit about X and Y to get your corner points. Here's a graph. It's only confirming what it appears that everybody is doing, which is really good. Here's a graph. It's just kind of your scale. If you kind of move those two, if you move them back a little bit, you'll make space for that triangle. It's just more of the scale that you used. So are you really thinking about those 3 corner points? Keep in mind that you know that X equals 200 on some of the points, and you know that Y equals 300. Now, I know some of you don't need to hear this, but I know some of you you just need to affirm that your corner points are right. And how do you get them? Again, take what you need. This corner point in the bottom left is just the intersection of these two constants. But each of these corner points uses one of those constants. So this one, I know that y is equal to 300. That means x has to be the rest of it. The rest of it has to add to 800. This one, I know that x equals 200. So the rest of it I can determine to whatever equals 800. I encourage you just to finish the process. You're kind of on the home stretch here. If this was like a graded problem, remember that you would want to make a little statement. It's your note, so it's up to you what you want to do. But could you make a little statement, a little sentence that shows that you understand what you just did? Here's the three prophets. It's probably not a surprise to you that the answer is going to be one of the points at the far top or far right. It's interesting that they're close, but it looks like it makes a little more sense to make more plywood. It makes more sense to make more plywood. If you think about it, you get more money from the plywood. You get $30 for every Y. So we're going to do 600 units of plywood and just 200 units of lumber, which is what you can write in your little sentence. Here's just an example of a sentence, and that'll get you that max profit of $22,000. It's an interesting process. It's known as linear programming. People actually do this. It would be interesting to see how they do it with probably a lot more variables. I would imagine there's many variables. In fact, my wife's friend's husband, his name's Rod, he said it as often. Do you know Rod? Yeah. He said that, and not surprisingly, there's many variables, sometimes 20 variables. But hey, a matrix can solve that type of problem. A computer can solve it. So it can be done. For what we're doing in the classroom, we're going to stick with 2 variables so that you can kind of visualize the process.